Hello everyone, I'm Master RK. This presentation is going to be an introduction to quantum physics. My take, my views on quantum physics in a nutshell, in a simple way so that everyone can understand. Let's move on. First of all, we'll see the differences between classical physics and quantum physics, say modern physics. When atom models were evolved many years ago, Rutherford suggested that the core of an atom, called nucleus, comprises of positively charged particles called protons and neutral particles called neutrons. And the negatively charged electrons were revolving around the nucleus of the atom. So what happens here is when the electron keeps on revolving around the nucleus of an atom, it continuously emits electromagnetic waves and eventually loses all of its energy and may fall into the nucleus of the atom, which makes the atom unstable. So this implies that life doesn't exist on Earth. But we all know that life exists on Earth. Such a thing cannot happen. So this leads me to a totally different field of physics known as modern physics or say quantum physics. Before we delve into quantum physics, let's discuss about the wave particle duality, which means, say for example, an electron or a photon existing as both a particle and a wave. So in this figure, as you see here, the electron exists as waves and of course as a particle. And this picture talks about the nuclear research happening in CERN, European Council for Nuclear Research, wherein they did discover a particle, say a God's own particle known as Higgs boson, by colliding two fast moving oppositely directed photons. Well, what do you mean by wave particle duality? What are the properties of a particle and what are the properties of a wave? When it comes to a particle has mass, momentum, it's localized. It's always in one location. When it comes to waves, it gets reflected, refracted, undergoes diffraction, polarization, interference, and it's always delocalized. It keeps on moving from one point to another point. It keeps propagating from one point to another point. So this is how you differentiate a particle and a wave. An electron, a photon, and several other particles do exhibit both the properties of a wave and a particle, which you call wave-particle duality. Let's move on to the introduction to quantum physics. In the year 1900, Max Planck suggested that every particle emits or absorbs energy in small pockets called quanta. Plural is quanta, singular is quantum, which cannot be subdivided further into smaller particles. Say, for example, when you take a desert or say a sea or an ocean. In a desert, the tiny small sand particles, or in a sea or an ocean, the tiny small water particles can be assumed to be what we call quanta. In 1905, Albert Einstein suggested that light waves are composed of small pockets of energy called photons. The energy of a photon is given by E is equal to h into nu, where h represents Planck's constant, given by h is equal to 6.626 into 10 power minus 34 joule second, and nu represents the frequency of the radiation. A photon and an electron, as I've talked about earlier, has a dual property, both the properties of a particle and a wave. Now let's move on to a single slit experiment and a double slit experiment. Say for example, there is a gun which shoots off colored balls onto a cardboard with a single slit. Some of the balls may pass through the slit in the cardboard and hit a screen, forming a pattern over here like this. Or they may bounce back when they hit the cardboard over here or over here. This is what is happening in here. Now let's move on. When it comes to a double slit experiment, as you shoot off the colored balls as earlier, the balls may pass through two slits. in a cardboard and may hit a screen in this pattern. So this pattern is what I expect when it comes to a double slit experiment. But this doesn't happen. What happens is like this. You get a totally different pattern from what I expect. Well, because the electrons, the photons, or the tiny balls that you shoot off as small tiny particles behave as particles over here in this region, and when they pass through the slits they get to behave like waves. So in this region they behave like waves, and in this region they behave like particles. I mean the small tiny particles like the balls you shoot or electrons and photons. That's the reason why you get a pattern like this. As you see it here, when you shoot electrons from an electron gun, when they pass through the double slit arrangement, they become waves and form a pattern on the screen like this. So when I observe them, they behave like particles over here. And when I don't observe them, they behave like waves over here in between the two cardboards and form a pattern on the screen like this by what you call overlapping of waves, as it happens over here in this region. Now let's see wave-particle duality based on Schrodinger's cat arrangement. There is a chamber or a room which hosts a cat. A radioactive material kept in the room, when it emits radioactive radiations, it gets detected by a Geiger counter, which then activates a hammer, and when the hammer opens a container which contains a cyanide solution, it releases a poisonous gas, and when the gas reaches the cat dies. Now here, when I don't look at the chamber, when I don't open the chamber and look into it, the cat exists in two states. State 1, it is alive. State 0, it is no more, it dies. It's dead. So this is how you explain wave-particle duality. So when I look at it, say for example an electron or a photon or say a proton, it exists as a particle. But when I don't look at it, I say it may exist as a particle or a wave. In the previous experiments, a single slit and a double slit experiment, it actually exists as waves. So here, when I look at it, I say it's alive in state 1 or it's dead, it's state 0. But when I don't look at it, it may exist in two different states. A wave function psi represents matter waves or de Broglie waves. What are these waves actually? So when an electron or a photon, which exhibits wave-particle duality, travels in the form of waves, those waves are what we call matter waves or de Broglie waves. So this wave function psi gives you information about the particle, which exists in the form of sine waves in wave motion, and it's based on Heisenberg's uncertainty principle. Well, what is Heisenberg's uncertainty principle? You cannot determine the position and the momentum of a particle simultaneously. You can either determine the position of the particle, else the momentum of the particle, but not together. So this graph represents the position of the particle along x-axis, its probability of existing in a particular position along y-axis based on quantum wave function psi. So what you see over here is the most probable position of a particle at a particular instant of time. As you see here, the wave function may collapse and exist as a particle in a particular position in space. So there are two sets of rules in quantum mechanics. When someone looks at, say, an electron or a photon, the wave function collapses and it exists as a particle. But when I don't look at it, it may either exist as a particle or a wave. In this case, it exists as waves. Now let's move on to quantum tunneling. In classical mechanics, when an electron or say an atom wants to cross a barrier and reach another state, it has to literally climb up the barrier and reach the other state. Well, that's what classical mechanics has taught us all about. But when it comes to quantum mechanics, when an atom or an electron wants to cross a barrier, the atom, or say the electron, drills a tunnel, ultimately drills a tunnel through the barrier and crosses the barrier to reach the other state. So this is what we call quantum tunneling. What you see here is quantum tunneling at its best. The position of an atom may change from one position to another position. That is, an atom can keep on changing its location from one point to another point through a barrier across. So it can walk across a barrier from one point to another point. So what you see here is a red colored region which represents the region of a high probability of an atom to exist in it, while a blue colored region wherein the probability of an atom existing in it is less. Now, one of the marvelous applications of quantum tunneling is what you can see in stars and sun. So what happens in the core of a star and sun is nuclear fusion reactions. So when it comes to nuclear fusion reactions, a hydrogen atom fuses with another hydrogen atom. But the problem is hydrogen atoms do contain protons, and protons are positively charged particles. So what do you expect to happen is an electrostatic force of repulsion which exists between the protons. But these hydrogen atoms will cross the barrier by what we call quantum tunneling, will fuse together, resulting in the formation of helium nuclei, and hence a large amount of heat energy is released out of it due to what we call nuclear fusion reactions, and therefore releases light energy, which we get as sunlight. And the only reason, only factor for life to exist on Earth, I would say, based on this, is quantum tunneling. Now let's move on to quantum entanglement. As we have seen it earlier, the principle of superposition presents two states of a particle, say an electron or a photon, as both a wave and a particle in state 1 or state 0. Here, a particle which has a spin along x-axis in one point on Earth, which exists in one point on Earth, may find a totally different particle with a spin along negative x-axis in another point on Earth, entangled with each other. So this is what we call quantum entanglement, as you see over here. So one particle may exist on Earth, say with a spin along positive z-axis, and you can find an opposite particle in another point on Earth with a totally different spin along negative z-axis. So this is what we call quantum entanglement. And this happens because of what we call superposition, multiple combinations of states 1 and 0, which we call quantum bits or qubits. Now let's move on to Feynman's number. So this is a mysterious number. At the same time, it's a fascinating number. Well, why? Well, because scientists have not been able to find out the actual mystery behind this number and the fascinating information about the number conveys to all the physicists and to all the students of physics in this world until today. Actually, it is alpha equal to square of charge of an electron over product of Planck's constant h and velocity of light c. It's equal to 1 by 137. So I would say this is an unknown number, well, because it is truly fascinating and mysterious at the same time. Well, you call it a fine structure constant. It represents the probability of an electron absorbing a photon. It relates three domains of physics: electromagnetism through an electron, relativity theory through speed of light, and quantum mechanics through what we call Planck's constant. Now let's move on to applications of quantum physics. Quantum physics gets applied and may get applied in quantum computing, quantum communication through quantum key distribution, quantum teleportation, quantum internet, and in designing devices such as diodes, microscopes, and chips. So I'll be doing a presentation on the applications of quantum physics through another presentation. Thank you all. Thank you very much.